Hello, this is Calculus 1, Lecture 8a, Linearization and its Discontents. My name is Scott Grizzard from the University of South Florida. Today, what we want to talk about is linearization. Now, the big idea is that what we're doing is we're making a function of the tangent line. So, if I have the tangent line here, y minus y naught equals m times the quantity x minus x naught. What I'm going to do is I'm going to add y naught to both sides so that y is now by itself. And then I'm going to make this a function. So if my function is f and my x naught is a, I'm going to wind up with the linearization of f, right? L of x equals f of a plus f prime of a times x minus y. So this is the linearization of f at x equals a. Now, why would I want to do this? Well, it turns out that if I turn the tangent line into a function, I can actually talk about the original function, f, in some interesting ways, and it segues into a bunch of interesting mathematics. So the first thing I can do is I can use it as an estimator, and I can even get better estimators by not only using the first derivative, but then taking more derivatives. So the first derivative is going to give me a linear estimation. But then in Calc 2, what you're going to do is you're going to add more and more derivatives to this thing in order to make it work over a larger period. So the first thing I can do is estimate. The second thing I can do is I can start looking at the ratio of the two linearizations. And that's going to give us a very interesting application called Lhopitals Rule. The intuition behind Lhopitals Rule is the ratio of the linearizations. I can also define things like concavity, which is going to be important for us in Module 3. And then once I have the linearization, I can talk about this dx and this dy as separate differentials in a very intuitive and interesting way. And we're going to introduce that today, but then next time we're going to kind of more explore that a little bit more. Okay, so it's a very rich topic. So let's start with an example. Let's consider f of x equals e to the x. So the idea here is that what I want to do is I want to talk about values near x equals 0. I want to estimate what's going on about this function around 0. Okay, so is there something I could do? I don't want to compute that. What can I do to get close enough? If I want to estimate f of 0.1 or e to the 0.1, and I want to estimate a bunch of things. So let's say I want to do f of 0.05 or f of 0.01 or f of negative 0.05 and things in this range. I want to talk about values that are going on around here. Well, it turns out that, for values that are close to 0, the tangent line is it's a horrible estimator for things like over here, the tangent line at 0. But for the tangent line, for values around 0, the tangent line is actually pretty close. So I end up sticking near this. And this goes back to the idea, that big idea that I had, that every function, every differentiable function is locally aligned. So let's write that down. So if I keep that in mind, that's the intuition about what's going on here. So let's actually do create the linearization function. What I'm going to need is I'm going to need f of x and I'm going to need f prime of x. And then what I'm going to need is f of 0 and f prime of 0. So what I do is I write the formula, right? LF0 of x, right? So LF0 means the linearization of f at x equals 0. Now, it's important that what I'm going to do is then I'm going to stick other x values into that linearization. So there's kind of two x's going on. So you need to separate them in your mind, right? I've got a linearization based on a point used to estimate other things. Okay. All right, so I want to estimate. So if I do the computation, I'm going to have e to the 0. F prime of x is e to the x because I'm starting with e to the x. So f prime of 0 times x minus 0. So this is going to be e to the 0 plus e to the 0 times x. Now that's going to give me 1 plus 1 times x, which gives me 1 plus x. So the line 1 plus x is our estimator. So if I throw in 0.1 into my estimator, I get 1.1. And if I throw e to the 0.1 into my calculator, I get 1.0517. So it's close, right? It's not close here, right? If I'm trying to estimate from 1, if I'm trying to use the estimator of 0 to get the stuff around 1, it's horrible, right? I'm off by, over 0.5, right? It's like 0.7. But if I'm talking about stuff near 0, where my estimator is based, right? Here's this 1 point, right? Here's 0.1, right here. If I'm talking about that, it's pretty close. 1.1's there. I mean, I could zoom in and get some difference here. There's, what my 1.055 or 1.052, and there's my, 1.1. It's pretty close. So near 0, my estimator works pretty well. Notice also that I can predict the direction here, right? Notice also that my estimator is running below my function. And that's going to be key later. So I know for this particular function that my estimator is running below. Okay. So again, what I did, I'm always going to get an underestimate with this particular function. That won't be true in general, but for e to the x, I know which way I'm going. So again, I've got the formula for the tangent line at x equals a, right? Y minus, so this is f of a, my y naught. My x naught here, so my y naught is f of a. My x naught here is a. The slope of this line is f prime of a. So when I move things over, right, I'm going to take this thing, I'm going to move it over here. I'm going to wind up with the linearization of f at x equals a of x. And again, that's a little confusing there. Equals f of a plus f prime of a times x minus a. And that's my formula. Okay. Now, just a notational note. If f is unambiguous, if we all know what f is, we're going to write LA of x. And we're going to ignore the f. And you've seen me do this a couple of times in Desmos when I'm doing tangent lines. And I just kind of, I know the base point might change, but I know that the function we're talking about is the same. Also, if it's unambiguous, I'll just write L of x. So if you look it up in your book just says L of x equals f of a minus f prime of a times x minus a. So if I know what the f is, I know what the a is, I'll just write L of x. If I don't need to distinguish between the others. Okay, so if we look at the graph of this function, again, here it is. Now, this is the estimator based on 1. Now, on 0, right? So at 0, 1, or at 0, f of a, I have here my linearization. LF0, Desmos won't let me do the comma, equals f of 0 plus f prime of 0 times x minus 0. Okay, that's for e to the x. Now, I can do others. So let's look at, if I did it for 1, let's turn these off. So if instead I wanted my point to be centered on 1, this is what my estimator would be. And notice my estimator for 1 would be horrible for 0. Right? If I'm estimating near 0, it's kind of bad. But if I'm estimating around 1, it's pretty good. Okay. I can also, if I want to, you can see here I've added some sliders, and there will be a link to this in the notes. I can go ahead and I can slide this around, and you can see the estimators at different points. Okay, which is just the slope of which is just the tangent line at various points. So those are my estimators. Okay, let's do another example here. Let's let g of x equal the square root of x. And what I want to do is I want to estimate the square root of 8 using the square root of 4 square root of 4 as my base point. Okay, and what you're going to get, and I'm choosing this right. If I was going for 6 or if I was going for 3, I'd get much better results here. But for closeness. But I actually want to emphasize this kind of little difference in here. So we're going to go ahead and do g of x equals the square root of x, and we're going to use a equals 4 or x equals 4 as my base point. Okay, so I'm going to need some data here, right? So let's just write down what f of x is. Okay, so what I did was I wrote down what f of x was and then f of 4, because I need f of a, f prime of x, and f prime of 4. And these should all be g's, not f's. Okay, so now that we have our linearization, we're going to plug in 8. So this is our linearization based on 4. Now what I'm going to do is I'm going to plug in to this function, not my original function, to this function, I'm going to plug in 8. Not the square root of 8, because what I want to estimate is g of 8. So now what I do is I plug in 8. So my estimate of the square root of 8 based on the linearization is 3. Now, how good of an estimate is that? Well, if I plugged it into my calculator, I wouldn't be the happiest person in the world with that estimate. Again, I'm a little bit far from my base point, but it's actually not bad, especially for some applications. Let's look at it. So here it is. This is my base point right here, 4, 2. I'll just put it in there in blue. Now, this right here is the actual value, or, the approximation of the actual value. 2.828. It's an irrational number, so that's the thing. Well, 3, it's within 0.2. It's not the greatest estimate in the world, but it's not bad. Okay? So, my estimate, a little bit off, but it's not horrible. Okay. So that's another example. Notice here also, just real fast, notice here that the tangent lines are running above. Okay. So notice that my linearization is always an overestimate. So I can do better. Okay. So the first way to do it is to choose a different base point for the linearization. So right now, I am using this linearization based on 4 right here. Okay, so there's this dotted line here, but that's pretty far. There's another perfect square just after 8, 9. So if I wanted to estimate the square root of 8, 4 might not be the one I want to use. Maybe I should use 9. So let's see what happens if we use a equals 9. So we're going to enable these. And I zoom in here. In fact, it's so much closer that it's right on top. I've got to have to zoom out. So if I base off, this was the basis. This was the estimate from 4. This here is going to give me a new estimate based on 8. And as you can see, it's right there. So my 8 is going to be much more, it's going to be much closer to my actual value. Using 8 to estimate the linearization, using the base point 8 is going to be much closer to my actual, the value I want. Another way to improve my estimation is to add another term. I can add a second derivative term and create a quadratic estimator. So what I'm going to do is I'm going to take my linear estimator and then I'm going to add another term. And that another term will be g double prime of 4. That was my base point. Times x minus 4. And I'm going to square it. And then I'm going to divide everything by 2. I'm actually dividing everything by 2 factorial, but 2 factorial equals 2. And that's going to give me what's called the quadratic estimator. And again, this is a Calc 2 topic, but we'll just cover it briefly. See, this was my linear estimator, right? It was 8, 3. This right here is my quadratic estimator. So at 8, I'm going to get 2.75. And compare that to the old 2.82. So this quadratic is getting me a closer estimation. The thing that's called is the Taylor polynomial. And you'll see this a lot in physics. And as I said, this is Calc 2 stuff. If you're taking physics, the reason I'm doing this is if you're taking physics next semester with Calc, you may hit Taylor polynomials in calc in physics before you hit them in calc 2. So I'm just going to cover them briefly. Notice here that the Taylor polynomial is f of a plus f prime of a x minus a over 1 factorial plus, and then I'm just going to add terms for this blah blah blah, the nth derivative of x times x minus a to the n all over n factorial. And if I do this, and of course notice that the first one is just the linearization, right? And if I do this, I'm going to get better and better estimators for longer and farther away. So let's look at something more complicated. Would we like to compute cosine of pi x over 4 plus sine of pi x over 2? Let's look at what that function looks like. This is what that function looks like. It looks kind of, it's an interesting function. A lot of sound wave things happen like this. They're additions of sines and cosines and stuff like that. And they're actually pretty neat. So let's look at the linearization here. If I wanted the linearization at 4 of this, that's what it would look like. Okay. Well, let's take the quadratic estimator is going to be this one. Okay. So let's actually write down what that quadratic estimator is. So what I'm going to need, I'm going to need g prime of x, I'm going to need g of x, g prime of x, and g double prime of x, and I'm centered on 4 again. I like 4. So I'm going to wind up with the cosine of pi 4 over 4. And I've done this example is I've done this because with the 4s, because I want these terms to start canceling. So each time one of the terms is going to go to 0. It makes the math a little easier. So here's the initial. Now, when I take the derivative of cosine is sine. The derivative of the inside is pi over 4. I know I'm not doing the whole written out chain rule. And if it was on a test, I would, definitely. But I'm just kind of just throwing out the numbers to kind of shorten the video. And then I take the derivative of this. I'm going to get cosine times the derivative of the inside. And then I do it again. I take the derivative of this negative sine. I get a negative cosine. And then when I take the derivative of this cosine here, I'm going to wind up with a negative sine. And then don't forget the chains. Right, so I did the chain rule once. I got pi over 2. Do it again. I get pi over 4 because I'm multiplying out. And so the linearization is this. It's negative 1 plus pi over 2 x minus 4. But this quadratic estimator is this thing here. Right? This is unpleasant. I mean, this thing is pleasant. This is slightly less pleasant, right? I've got the original, I've got the negative 1. I've got the quadratic estimate. I've got the linearization right here. And then I've added this quadratic term. So what I'm going to wind up with is this equation, and this is what it looks like, right? There's my linear estimator, there's my quadratic, there, and then I can go farther, right? So with Taylor polynomials, I can go farther. So let's look at this again. Again, this is the quadratic. Here's the cubic. For example, this would be the quintic. I'm sorry, the quartic. This would be the quintic. And beyond that, I don't know the Latin, or the Greek, so, just bear with me. So there's the 5th degree. There's the 6th degree, not a lot of difference. The 7th degree here. And then I've got, I only did up to 7 degrees. So each time I'm just adding another derivative term. Let's look at a major implication of this linearization idea, and that's Lhopitals Rule. Now, we suppose I want to compute the limit as x goes to pi of sine of 2x over 4x squared minus 4 pi squared. That would be unpleasant. I could do it with the special limit. I'd have to transform sine into, I'd have to move sine over because sine is modulo 2 pi. So I'd have to add 2 pi to the thing and then kind of futz with it. I think it's 4 pi to the thing and then kind of futz with it. But I could do it. It would be unpleasant. But let's instead say, okay, I want to find the limit of this function as I go to pi. I'm going to wind up with 0 over 0. It's unpleasant. this is what that function looks like here. And I've got a nice little hole here at pi, which is what I want to talk about. Well, instead of looking at r itself, this is, I want to compute the limit of this thing. I'm going to call this thing r of x that I want to compute the limit of. Instead of looking at that limit, let's instead look at the two things, the thing on the top and the thing on the bottom. The thing on the top here is f, and the thing on the bottom is g. And as you can see right here, at pi, both functions equal 0. Well, what happens if I instead look at the ratio of their linearizations? So these are the two linearizations, right? These are the two functional tangent lines. And as you can see, this one for g is pretty steep. But instead of looking at pi, remember, I want a limit. So I want to talk about what's going on around pi. Well, if I take this thing and divide by this thing at the same x, I'll actually come out with a number. And then what happens if I take the limit of the ratio of these linearizations? Okay, let's look at that. So that's the big idea. I want to look at the ratio of their linearizations centered on pi. So again, if I zoom in close enough, both the numerator and the denominator become this. So what I'm going to say is that the limit as x goes to pi of sine of 2x over 4x squared minus 4 pi squared is close to the limit as x goes to pi of L of f of pi of x over Lg. So I want the linearization of f over the linearization of g. Well, what happens when I do this? Okay. Well, I'm going to need f prime of x, which gives me 2 cosine. I'm going to need g prime of x, which is simply 8x. Right? This is f is sine 2x, and g is 4x squared minus 4 pi squared. So I'm going to do both derivatives. Okay. Then I'm going to take f prime of pi and g prime of pi. So I get 2 and 8 pi. Now notice here, f prime of pi, f of pi and g of pi, not f prime of pi and g prime of pi, but f prime of pi and g prime of pi are 0. So they go away. And what I'm left with is the limit is f prime of pi over g prime of pi, f prime of pi times g, this term, which is that term there, and that term and that term. Well, both of these terms have an x minus pi in common, so they cancel. And all I'm left with is the limit as x goes to pi of f prime of pi over g prime of pi. Well, that I could compute. That's 1 over 4 pi, right? That's 2 over 8 pi or 1 over 4 pi. So I can compute that thing very nicely. So what I say is that if f and g are both 0 at a, and that was a key step here, this right here, the fact that these two things equal 0, that's a key step, right? Both of those things equal 0. They cancel. They go away. They don't even cancel. They're not canceling with each other. They're just 0. Okay? They're just gone. So here's my Lhopitals rule. If f prime of a and g prime of a both exist, and g prime of a doesn't equal 0, and f of a equals 0 and g of a equals 0. So both of them have to be differentiable at 0. G prime of a can't equal 0 because then I'd wind up dividing by 0. And both of the functions, when evaluated at a equals 0, then the limit as x goes to a of f of x over g of x is simply the limit of the derivatives. And if you get any limit problems on test 2 where this is applicable, you can now use it. Okay, because we've covered it. So if you meet the conditions for Lhopitals rule, you can now use that on test 2. We will do a fuller Lhopitals rule. Someone's going to immediately say, well, wait, this thing doesn't have to be true. You're right. There's a stronger version of Lhopitals rule which says that we can get rid of this condition. So now let's look at differentials. Now, differentials are one of those things that are totally optional for Calc 1. they are nice if you do things. So let's look at the idea is we're going to just nudge both things a little and then solve for dy over dx. So what I'm going to do is I'm going to generate these differentials by the chain rule. So let's just look at what's going on. Okay. So here we go. I'm going to take y equals dx. I'm going to take the derivative of this side, but I'm just going to let it generate a differential. And now what I'm going to do is solve for dy over dx. So I'm going to move the dx over to this side, and I get dy over dx equals 2x. That's the idea. Okay, here's another example. I've got 1 equals y squared plus x squared. So what I did was I just implicitly differentiated, and every time I took a derivative, I just left a little dy or a little dx, depending on whatever I was differentiating with. So I just keep doing the chain rule in line. And then you solve for dy over dx. That's a neat trick. It's also going to let us get at it's going to give us a nice intuitive approach to approaching inverses. Last thing we want to talk about is concavity. So remember, I kept mentioning this idea that, for e to the x, originally, my tangent lines, my linearizations were running below, right? And they were running below for the whole function. Whereas for the second example, when I did the square root of x, my linearizations ran above. Okay? This actually means something. And what we're going to call that thing that it means is concavity. So the way we're going to define concavity, okay, in this class, for functions that are differentiable, we're going to let f be differentiable at x equals a. We're going to say f is concave down at x equals a if for all x near a, f of x is less than Lf of a of x. So I'm concave down at a if for everything nearby, the linearization gives me an overestimate, or f is under the linearization. Now, of course, concave up is the exact same thing, except reverse. For all x near a, f of x is above the tangent line, or the linearization is already an underestimate. And that's the definition of concave up. Okay, and we can see this if we just want to look at an example here of a function that's both, that is over different areas, switches its concavity. Here I've got f of x equals x cubed minus 3x squared. If I'm in this territory here, right, this is nice and concave up, right? The tangent line is running below. However, this, if my a is over here, the tangent lines are running above. If I'm less than 1, my tangent lines are above, right? So that is concave down, right? Because I'm always getting an overestimator. And there's this point where it switches, and that's called the inflection point. And we're going to see that right here, if I make it 1, right? This is the inflection point. And if you look at the inflection point, on one side the tangent line is running above, and on the other side the tangent line is running below. So here it's running below, here it's running above. My concavity is changing. And that's kind of interesting. So that's going to be something we're going to talk about in Module 3, which is concavity. Okay, just to go over what we went over, just to review what we went over, we talked about linearization as the functional form of the tangent line. We used it to approximate some things. We did Taylor polynomials briefly, Lhopitals Rule, the diet version. We're going to do more of Lhopitals Rule later on in the class. We talked about differentials and this idea that I could just differentiate everything using the chain rule and then solve for the ratio of the differentials. And then we defined concavity. So next time what we're going to talk about is functions and inverses. Everything here, this is the start place where test 2 information ended right here. Everything that we covered after that stuff, the Taylor polynomials, the Lhopitals rule, differentials, and define concavity, is all test 3 material, but you can use Lhopitals rule, the diet version of Lhopitals rule on the test if you show that it meets the conditions. Okay, that's it. I'll see you next time. Bye.